Okay, ninth graders, today we're going to start talking a little bit about electricity and magnetism. This is going to be the final unit that we do this year, but it's still part of the same unit we've been working on. We've been talking about work and energy, and now we're going to talk specifically about electrical energy and how we can create electric current at the power plant. So the first thing we have to understand is this idea of electric charge. And we've been talking about that since the beginning of the year, back when we talked about atoms, and we talked about how there are protons and electrons, and how protons are positively charged and electrons are negatively charged. The thing about charge is we don't really know exactly what it is. We know things about it. We know characteristics of it, but why do things have charge? And what is it really? We don't really know. We just know that it's a fundamental thing that everything has. Like love, hard to define, but you know when it's there. All right, we know charge is conserved, just like energy and mass. We know we can't create or destroy energy. We know we can't create or destroy any mass. And the same is true of charge. We can't create or destroy charge. We can only move it from one place to another. We know that like charges repel and opposite charges attract. Again, we talked about that. That's called the electrostatic force. So here, say this is a negatively charged ball and a positively charged ball. They will attract to one another, but like charges will push each other apart. We call that repelling. Now, around any charge, you have what we call an electric field. Just like around any mass, you have something called a gravitational field. And if you have enough mass, you have a strong enough gravitational field to really notice it, like the Earth. Okay, you have a gravitational field, but because you're not big, that gravitational field is not noticeable. For charges, every charge has its own electric field around it. Now, the thing is, electric fields are way stronger than electric fields are way stronger than gravitational fields. It's just that usually they're created by such tiny, tiny things that their force per mass is much greater, but the masses are so small that we still don't necessarily notice them. Though we do feel electric fields. Put your hand next to a TV screen, or stick your hands in the dryer after you dry your socks and see how they stick together. Feel that the electric field make the hair on the back of your arm stand up. We measure charge in a unit called the coulomb. And a lightning bolt has about 10 coulombs of charge. So a coulomb is a huge amount of charge because we know how powerful lightning bolts are. One electron or one proton, they each have the same amount of charge, even though protons are much bigger. And that amount of charge is 1.6 times 10 to the minus 19th coulomb. So again, just a super, super tiny amount because these things are so small. Now, most matter is neutral because the number of protons that an object has is equal to the number of electrons that you have, and they cancel each other out. When you have an imbalance, the charges will try to move to make things equal. Now, charges can move in things called conductors. Conductors basically are metals where you have free valence electrons. Insulators, things like plastic and wood, gases, they don't conduct charge very well. And typically, again, those are made out of nonmetals. And the last thing I want to talk about today is static electricity. So like I said, if you get a buildup of one kind of charge on you, typically it's only electrons that do the moving. Those electrons want to move and get away. And so if you shuffle your feet on the floor and you gain more and more electrons and you go and touch a metal doorknob like this, you see that little spark there. That's an example of static electricity. Your body collects them, and then they will conduct once there's enough of a charge imbalance between you and another object. All right, that's it.